Welcome to Finite Element Methods Abacus tutorials. I'm Leonardo Araque, a PhD student at UCLA, and I will guide you through this tutorial. The purpose of this tutorial is to model a blisk. This is a rotor disk composed by 45 plates with a speed, with angular velocity of 12,000 RPM. The plates are made of titanium alloy, with density, Young's modules, and Poisson ratio provided in this slide. Let's start the modeling in Abacus and to extract the modes of vibration. Since this is axisymmetric rotational part, we already modeled this part, and we're using this axisymmetric condition for this blisk to model only one of the plates, and later we can present the entire rotor disk with the 45 plates. So starting from the given part, the next step is go to the module property and input the material properties. Since this is a titanium alloy, let's call this titanium alloy. The density, according to the data, is 4430 kilograms per cubic meter. And the mechanical elastic properties are the Young's modules, 119 gigapascals, and the Poisson's ratio, 0.342. Next step in the same module is to create a section. This section is a solid homogeneous. Make sure to select the material. Next step is to assign the section to the part. We select the entire part. We make the selection of the section we created. And once the part turns green, signs that the section has been assigned to the part. In the next step will be to create an instance. To create an instance, we select a dependent instance. And for future use, I'm gonna move to interactions. Or actually, let's continue in order with the next step. Let's go to the module step. Let's create a step. This step is a static general step. Just accept the conditions in this window. And we can create the second step to extract the modes of vibration, the eigenvalues of the dynamic problem. So the second step called modes. In the procedure type, select linear perturbation and make the selection frequency. We are interested only in the first 6 modes. And accept the other conditions. If we go to the step manager, we can see the three steps: the initial step, the step number 1, and the step to extract the eigenvalues. Now we can go to interaction. So in interaction, we need to create 2 reference points to later apply the cyclic symmetry condition to this problem, to simulate the effect of the 45 plates in the rotor disk. So let's create these points. The first point is located at the origin. So give the coordinates 0, 0, 0. And the second point is along the z-axis, which is gonna be the rotation axis for the plates. So we can just give the following coordinates. So now you can see the 2 points we have created. Right, it seems that accidentally I created 3 points, so I'm gonna eliminate one of them. So go to assembly, instances, no, actually features, select the point number 3 and delete it. So we only leave 2 points in our selection. All right. So the next step is create an interaction. So to create an interaction number 1, select the step initial, actually step 1. Let's select the step 1 and then look for sorry, it was a step initial, and then look for the selection of the cyclic symmetry. We need to select 2 surfaces. So to select the master surface, apply the left view and select surface, and in the CAD model, select this surface. When this is done, we are required to select as left surface. So again, in the selection, click on surface. This time, rotate the part to the view CY, negative C, positive Y, and make this selection. Now we are required to select the first point of the axis of symmetry. So let's select point number 1 as the first point. And let's select now the second point in the axis of symmetry, which is the reference point number 2. Okay, in this way, we are creating the cyclic symmetry to the model. So only what is left is to input the number of sectors, the number of plates, which is 45, and accept the other conditions. All right, so each blade is distributed every 8 degrees. So that will complete, the 45 blades will complete 360 degrees components in the rotor disk. So the next step is in the module load. We are creating we're gonna create a load. This load is in step 1. We want to apply, to simulate the effect of the centrifugal force. So for this purpose, we need to go to mechanical, look for rotational body force, and make the selection. The load applied to the entire blade. So select the entire blade. And now you can enter the coordinates for the first point on the axis of rotation, which are, the first point is at the origin, so just accept this. And the coordinates for the second point are 0.1, which is the coordinates corresponding to the reference point number 2. So you can either select the point or just input the coordinates. In the edit load dialog box, you can see that the 2 points, point 1 and point 2, to determine the axis of rotation, you can see the coordinates for these 2 points. Now, we're looking for a centrifugal load effect, right? And the magnitude of the angular velocity in radians per time would be 1256 radians per second, which is equivalent to 12,000 RPMs. Okay? The next step is to apply the boundary condition. So to create a boundary condition, we select the step number 1, mechanical, make the selection of displacement and rotation, and now select the region to apply the boundary condition. So we assume that the surface connecting the plate with the rotor disc is completely constrained. So it means that the displacements in the 3 directions are 0, right? And that's all the boundary condition we're assuming for this model. All right, the next step is in the module mesh. We're going to select the mesh for this part. First, switch to part, and then go back and set the part. The approximate global size for this model is 0.006. And the element type from the element library, select standard, 3D stresses, and the geometric order of interpolation is quadratic. Toggle reduce integration, and make the selection of tetrahedron elements. So the element is 10-node quadratic tetrahedron for this model. Let's go to mesh controls, make the selection of tetrahedron, and click done. Next step, mesh the part by accepting the condition. And in the message window at the bottom of the screen, we can see that almost 29,000 elements have been generated for this part. So finally, we need to go to the module job to create a job. Let's give it the name job list. Continue. And okay. The next step is just to submit the job for analysis to obtain their results. Once this job has successfully completed, we can see the displacements for the blade, and we can see the modes of vibration for, let me start from the first one. So the first mode of vibration, the second mode of vibration, third, fourth, fifth, and the sixth, number 6. If we want to see the blisk, what I mean is the rotor disc with the 45 blades, you can go to View, select ODB display options. In this ODB display options dialog box, select mirror pattern. Make the selection of the axis of rotation C and input the number of blades, 45. That will give us a total angle of 360 degrees as explained earlier. Accept the rest of the other conditions and apply. So now you can see that the blisk, you can see the blisk with the 45 blades. All right, so by applying this cyclic symmetry condition, we have saved a lot of computational time. Now, we could run this model considering the nonlinearity in the geometry to see that we need to come back and redefine our load step. In the module step, we can go to the step manager and redefine in the static general step the nonlinearity in the geometry by toggling on and then accept this condition. Now we need to come back to the job and run the job again to see the results. If the results compared to the first time we run this model don't vary significantly, we could say that the nonlinearity in the geometry doesn't have an effect in our model. So if we start switching between modes and comparing these results with the original results, we can see that for all modes, there is a significant increment, which means that for this case, the nonlinearity in the geometry plays an important role. With this result, I conclude this tutorial.